You know, you think that in math, the easiest thing you can do is count, right? I see one thing, I see two things, I see three things. But it turns out that when the counting gets a little bit more intricate, it's much harder to do. Counting turns out to be really hard, and actually is an entire area of mathematics called combinatorics. So in combinatorics, one tries to count things systematically. So the hard part about counting is that you want to make sure that you count all the options, and you only count each option once. Therein lies the rub. So let's take a look at a variety of issues where counting naturally arises, and you'll see that, in fact, it's not as easy as it first appears. Let's start off by taking a look at something that goes on at Travis High School, and maybe at high schools near you. So students at Travis High School can choose one physical education elective, one fine arts elective, and one foreign language elective. And the question is, how many different schedule choices are there? So let's take a look at the different electives. So for physical education, there are two electives. There are individual sports and team sports. You can do one of each of these. You can pick one of these. Fine arts, you can pick one of these. Art, music, drama. Foreign language, you can pick one of these. Spanish, French, sign language, or Japanese. So we're allowed to pick one from here, and one from here. And the question is, how many different ways are there picking? Well, we can do it in a variety of ways. Let's just sort of think about it just once together. We can start off by thinking about an individual sport, select that one, select art. Now, with those two choices fixed, how many possible schedules are there now? Well, now it's clear. There are 4, because I could have this in Spanish, this in French, this in sign language, this in Japanese. Those are all different. So I've got 4 different ones for this set. Alternatively, I could have picked the individual sports and music. Well, then how many would I have? How many new options would I have? I'd have individual sports, music, and, well, there are 4 options. Spanish, French, sign language, Japanese. So there are another 4 that we can sort of toss on. So now we're up to 8 possibilities. And then finally, what happens here with the individual sports and drama? Well, I could have individual sports, drama, and, well, there are 4 possibilities. I could have Spanish, French, sign language, Japanese. So there's going to be another 4, and so now I see I'm up to 12. But I'm still not done, because that was all assuming I was picking the individual sports. What if I picked the team sports instead? Well, then I got to start all the way over and say it's team sports and art, 4 possibilities. Team sports and music, 4 possibilities. Team sports and drama, 4 possibilities. So that gives me another 12, which gives me a total of 24. Wow. So it turns out there are a lot more schedules than we might have first thought. How can we find that systematically? Well, there's actually a really neat way of doing that called the fundamental counting principle. So the fundamental counting principle says that if I'm supposed to select one thing from, in this case, 3 piles of stuff, and there's so many in this pile, and so many in this pile, and so many in this pile, to know how many possible ways there are of picking one from each thing, I just take the number of things in this pile, multiplied by the number of things in this pile, multiplied by the number of things in this pile. So in this case, I would see 2 multiplied by 3 multiplied by 4. Let's compute that. If I take 2, because there's 2 things here, multiply that by 3 things here, and multiply that by 4, what do I get? I get 2 times 3, which is 6, times 4 is 24, and that was the answer we knew was correct. So you can see an example where the fundamental counting principle actually works. So if you've got a bunch of things, and you've got so many items in each of those things, and you want to pick one item out of each, how many different ways are there of picking them? To count that question, you just take the product of the contents of each of the containers, and you've got it. And you've got it. Let's take a look at another example. So here we go. So a student ID consists of 2 digits, so that means 2, 5 and 3, 0 and 1, followed by 5 letters. Now, so that we don't get confused with 1 and 0, we're going to actually remove the letters I and O, because they kind of look like 1 and 0 sometimes. So there's no I, no O possibilities. And each letter or number may be used more than once. So we could have 1, 1, A, so forth. The question is, how many different student ID codes are possible? So what's the deal? The deal is we're going to have 2 digits followed by 5 letters. So let's use the fundamental counting principle here. We have 2 digits followed by 5 letters. So what do? I can pick any one of how many digit possibilities are there? Well, 0 through 9, so there's 10 possibilities. I take the total number of digits for the first digit, multiply that by the total number of possible digits for the second digit, which is also 10, and then I've got 5 letters. So what I do is I take the product of the number of possible digits times the number of possible digits, that's the 2 digits, and then I've got 1, 2, 3, 4, 5 letters, and so I take the number of possibilities for the first letter, second letter, third letter, fourth letter, and fifth letter. I'm allowed to repeat letters, so how many letters and digits are there possible? Well, here we know there are 10, and there are 10 possible digits for the second choice. Now, what about the letters? Well, we know there are 26 letters in the alphabet, but don't forget, I and O are not allowed, so there's actually only 24 possibilities. And there's 24 possibilities for the next letter, 24 possibilities for the next letter, 24 possibilities for the next letter, and 24 possibilities for the last letter. So this actually works out to be 100 multiplied by 24 raised to the 5th power. But what does that equal? Well, of course, I can do that in my head. Can you do that in your head? I can do it. It's going to be 796,262,400. Is that what you got? Well, that's correct. So look at that. There are a lot of different possible IDs. If a school actually used this system, you can see they're not going to have to worry about 2 students having the same idea. You can go for years and years and years and years and never actually start over with the ideas because you have almost 800 million possibilities. Counting is tricky, and we've got to be careful. The numbers get big pretty fast. Let's take a look at another tricky counting question. So here we go. So 7 people auditioned to be in a play. The question is, how many different ways can the director choose to fill 4 roles from this group? So we have 7 different people and 4 different roles. Well, here you see I want to take these 7 people, and there are lots of ways of picking 4 of them. And then every time I've picked 4 of them, like you, and you, then I've got to pick out which of the roles they're going to take. So suppose I've got 4 roles. I've got the king, the queen, the prince, and the maiden. Well, if I have 4 people, there are a lot of ways of putting them toward those roles. So there's lots of complicated way of counting, lots of possibilities, and we've got to count them all. Well, this is an example that actually is referred to as a permutation because the order matters. I have different characters that can be taken on by any one of the 7 people. So in fact, I've got to take a look at how many different ways there are of selecting 4 people from 7 when order actually matters. So, Mary, Jane, Todd, and Chris is different than Chris, Jane, Mary, and Todd. So the order is going to matter because, of course, they might be actually taking on different roles. So to compute that, we use what's called the permutation. Let me show you the formula for this and the notation. It looks a little foreign, but we can figure this out. I promise you it's not a big deal. It's important. The hard part, by the way, let me tell you what the hard part is. The hard part's not the formula. The hard part is knowing to use the formula. Really. So it's the thinking process to realize that, in fact, order matters here. All right. So here, this is the permutation where we have n things and we want to choose r of them. So we have n things. We're going to pick r of them. So r is always smaller than or equal to n. And order matters. So this is the permutation. And it equals this thing. And you first think, oh, wow, it's a fraction where we should be very excited. We should say n divided by n minus r. Well, no, this is not an exclamation point. In mathematics, this is actually called a factorial. Let me just remind you what a factorial is. It actually is a really big product. So it's a shorthand way of writing a really big number. For example, if we take a look at 5 factorial, what that means is it's the product of all the natural numbers from 5 down to 1. So it's 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. So that huge number is 5 factorial. So maybe actually it's worth saying 5, because actually it's really, really big. So given that as the definition for the factorial, we see that this ratio of factorials will produce the permutation n choose r where order matters. So in this case, I've got 7 potential actors. I've got 4 roles. Order matters. So I want to look at the permutation 7 choose 4 order matters. And so what is that? Well, this formula tells me it's 7 factorial divided by 7 minus 4, which is 3. Got ahead of myself there. Now, sometimes these actually simplify. In fact, all of the time they simplify. Let me show you that this actually simplifies by writing this out. 7 multiplied by 6 times 5 times 4 times 3 times 2 times 1. But look what's happening in the denominator. I see 3, which is 3 times 2 times 1. And you can see that, in fact, this simplifies. All of these factors get canceled away with all those factors. I'm left with an invisible 1 downstairs. And so I'm just left with what? Well, I'm left with 7 times 6 times 5 times 4. And so that's going to be 210, that's this thing, multiplied by 4. And I see a 0, and then I see a 4, and then I see an 8. So the answer is 840. So there are 840 ways of doing this. And you can see how we computed this. We have four parts. And orders matter, they're different parts. And I've got to select 4 of those people from the 7. And so I see 7 factorial divided by 7 minus 4, which is 3 factorial. And when you figure this out, you get 840. Neat. So we just saw an example where, in fact, the order matters in terms of how we're selecting people for a play. But sometimes order doesn't matter. Now, can you imagine a scenario where you're picking things out and order doesn't matter? Well, here's one. So Marcia's going to choose 5 flowers from a bouquet of 12. How many different ways can she choose the flowers? So what I'm assuming here is that Marcia's going to make a new bouquet just using 5 flowers. And so she's going to pick 5 from 12. So what we got here is a beautiful bouquet of flowers. Quite attractive. I can hide. Can you see me? Yes, flowers are useful because you can hide. So in fact, if you want to hide in the back of the class one day, just bring a big bouquet of flowers and the teacher will never see you. Anyway, Marcia's going to pick some of these flowers to make a new bouquet. Now suppose she picks the purple one and this dark one here and the rose. Okay? Now she's going to pick 5, but let me just pick 3 here for now, if I can. Now, of course, there's lots of ways she could pick them. She could pick the rose first, and then the dark flower, and then the purple flower, or the purple and so forth. But once she takes them out, and she puts them and makes her new bouquet, no one's going to ever know how she picked them out. So the order here doesn't matter, since she's going to take them and just look at them as a collective whole and make a new bouquet. So the bottom line here, here's an example where picking out the rose, this flower, and that flower should count the same as first picking out this, or this, or first picking this, or this, or first picking this, then this, then this, or this, and this. Lots of ways of doing it, but they're all the same. It's all the same bouquet. So here, the order doesn't matter. Well, when you want to count picking things out, when order doesn't matter, then in fact, we call that a combination. Okay? When order matters, we call that a permutation. When order doesn't matter, we call it a combination. Now let's think about it. Should a combination be bigger or smaller than the same permutation? Well, if order matters, then once I pick out these 3 flowers, there are lots of ways of picking them out. So a permutation would be kind of big. But a combination would be smaller because I don't care whether I pick the purple, the red, or the orange, or orange, purple, red. They're all the same to me. So I don't care about it. I'm just going to count that as 1. So all the stuff that we were counting separately before now count as 1. So a combination is going to be smaller. A combination is going to be smaller. Let's see if we can actually compute it. Well, we can figure that out because we can just start with what we know, the permutation. And so let me show you the formula for a combination. So this is the notation. We say the combination of n choose r. So I have n things. I want to choose r of them. So r is going to be smaller than or equal to n. And the rule is that I'm going to select these R things, but the order doesn't make a difference. I don't care how I'm picking them out. I'm making a bouquet. No one's going to know what flower I picked first. And the recipe is this. Now, notice first off that right there is the formula for the permutation N choose R, where order does matter. But since the order of picking the R thing doesn't matter, what we do is we just divide through by the R factorial in order to not count all those extra ways of doing it in different order. So in fact, you can see this is smaller than that, which was the permutation. So in this case, what's Marcia doing? She has 12 flowers. She's going to pick 5 of them. So we write this out as saying 12 choose 5 things. What's the definition? The definition is 12 factorial divided by 5 factorial. We multiply the 5 factorial by 12 minus 5, which is 7 factorial. Now, if you write all this out, what do we see? So let's write this out. 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Phew! Divided by 5 times 4 times 3 times 2 times 1. And now I'm supposed to write 7 stuff. But think about it for a second. What is 7 factorial? It's 7 times 6 times 5 times 4 times 3 times 2 times 1. So in fact, that 7 factorial right there, we can see can be simplified with all of this. And so I'll do that. Now, in fact, you can actually simplify yet further. Let's see if we can actually simplify a little bit further. Like the 5 multiplied by the 2 gives me a 10. So that can actually simplify with this this factor of 10 on top. And so I see the 5 and the 2 can combine with the 10. Actually, the 4 times 3 is 12, so I can simplify that with the 12. And I seem to be just left with the 11, the 9, and the 8. So now it's a small number. We can actually put this in on a calculator or do it ourselves. So 11 times, and that's 72. And this we can actually really do in our heads. Yes, you can do in your heads, because 10 times 72 is 720, and 1 times 72 is 72. When you add them up, you see 792. So yes, you can even do this big thing in your head for real. No one would ever doubt you, because the number is now so small. Anyway, the point is you can see the difference between a combination and a permutation. A permutation is where you're trying to select things out of some collection, and the order of selection actually matters. And a combination is a smaller number where, in fact, the order doesn't matter. Using the formula is really not that hard once you realize all the products can be simplified a little bit. The hard part is looking at the issue and determining whether order matters or order doesn't matter. That's the trick. As long as you keep that in mind, you can count anything you want. I'll see you soon.